This is Rescue Shuttle Control again. You've done a great job at implementing your keyboard input capability, and that means that we're all ready to add the next level of functionality to your system. And this will involve a new hardware component and a little bit more software logic. So we're building on our knowledge and doing a great job. Today, we're going to add to your ability to input data using your keyboard the ability to get audio feedback. And so we're going to be using a sound producing element in the circuit today. So to start off, let's introduce this new piece of equipment. You'll see it here. This is a passive buzzer. Now, the fact that it's a passive buzzer just means that it doesn't have any internal intelligence. It really just responds to the inputs that we send it from the Hero and doesn't do any internal logic of its own. But it will be very useful for us in being able to produce a variety of sounds that are encoded by the information that we input on our keypad. You'll notice something about this buzzer as I'm showing it to you right here. I've got one here in my hand. There's another one that's already installed on our breadboard right here, but it's a little harder to see its connections. You'll notice that there are 3 leads on this buzzer, but we're really only using the 2 outside leads. This particular buzzer has the 2 leads labeled with a plus and a minus. Your buzzer may look like this, or it may be different. Instead of having a plus, it may say S for signal, and for minus, it may say ground. But in any case, this indicates how we should hook this up to the Hero so that it will produce sounds as desired, with positive going into the plus input and negative or ground to the minus input. That's how we've hooked it up here on the breadboard, and we'll talk about that in a little bit more detail right now. Of course, this will all make more sense when we talk about it in the context of the software that's driving it. But for the moment, let's just be clear on what we're trying to accomplish here in connecting it to the Hero. We have a very simple circuit on the breadboard here today, consisting simply of a positive connection, in this case coming from pin 10 of the Hero, which you'll remember from last time we didn't use pin 10, and so it was available, and it will be available to us to program as an output. So with this orange wire, I've connected pin 10 to what is the positive terminal on the upper side here of the buzzer. And then the negative terminal of the buzzer completes the circuit with this white wire that connects to ground. I've provided a ground connection on this bus right here on the breadboard by connecting it in turn with another white wire to the ground of the Hero. So the buzzer will function when we are able to command pin 10 to high volts or low volts, depending upon what's going on in our Hero code. The rest of the circuit that's hooked up here should be very familiar to you because it's identical to what we did last time in using the ribbon cable to connect the keypad to the pins of the Hero. So, with that little hardware introduction, it's now time for us to turn our attention to the software that we'll be using in order to program and obtain output from this audio buzzer. Let's look at the code. Right now, what you're seeing in the code here should look identical to you to what we did in our last session. You'll see some very familiar things there. At the top, you'll notice that once again, we've included the keypad libraries because that's what we need in order to be able to access the functions that read and interpret keypad punches. You'll also see a set of variables that we've encountered before. We have our constant variables that just fix the number of rows and columns on our keypad, which in this case, it's a 4x4. And you'll recall that we introduced some arrays. We have these one-dimensional arrays, the row array and the column array, that basically associate pins with rows and columns. And as you remember, if you go back and review our last session, we arranged the row pin numbers in descending order and the column pin numbers in ascending order in order to get our association of buttons and values to comply with our usual convention, which is that the keypad begins in the upper left and ends in the lower right, as opposed to beginning in the lower left, for example. So that's the reason why we chose this particular row and column ordering. Next, you'll remember that last time we associated each combination of row and column, 16 possible combinations, with a character. So this would be the character that you would get when you pressed a particular button. And we chose those characters to be the numerals 1 through 9, and then 0, and then the special characters star, hashtag, A, B, C, and D, arranged in this keypad arrangement. So put in some comments here to remind us what was the first row, second row. So for example, if I come over to my keypad and I press the third row and third column, that would correspond to the number 9 right here. Oh, and one more thing, which is review, is that we used the keypad library functions to define our own keypad structure, our own keypad variable. And so we named it MyAwesomePad, and we defined it and activated it using the makeKeyMap function. So after we've made this call, MyAwesomePad will now correspond, it will now associate the button characters that we've identified up here in the array of arrays, buttons, with the particular rows and pins that are pressed. All right, so now we move on to something new. In addition to being able to construct a two-dimensional array that associates characters with each button on the keypad that's pushed, we now want to associate a sound with each one of those buttons. And so we have defined another array of arrays, another two-dimensional array, 4x4. So just as the characters that we called buttons, here we're going to create not an array of characters, but an array of numbers, an array of integers called tones. So each one of these numbers, you'll see there's 31, 93, 147, and so on, all the way up to the lower right-hand corner, which is 4,978. Each one of those corresponds to a frequency. Each one of those buttons, when pressed, will then be associated with one of these frequencies. So what does frequency have to do with anything? Well, when we have the hero command the buzzer to make sound, what we're actually doing is sending it a square wave of voltage, on and off in the shape of a square wave. This is actually rather similar to the way that we commanded the pulse width modulation to light up our color LEDs. Instead now of getting different light intensities, we're now going to be getting out different sounds as we command a square wave to go out, in this case, over pin 10. Now, each one of these numbers corresponds to a certain number of hertz. 31 hertz would be a low frequency. 587 hertz would be a moderate frequency. 4978 hertz would be a high-pitched frequency. So we should expect when we run this code and we press the buttons that we'll hear successively higher-pitched sounds as we go up the scale here on our keypad. So we'll check and see if that actually works the way we're expecting it to. All right, so we now see there's a one-to-one correspondence between buttons pushed and the characters and the frequencies associated with those buttons. One more little bit of housekeeping that we have to take care of. We'd like to define a variable that will correspond to the pin that the hero is going to use to activate the buzzer. So we've just defined the integer buzzer here to be 10, and so that means it'll correspond to pin 10. And you'll see that, yes, indeed, we did use pin 10 on the hero to drive the buzzer. So hopefully that will work as intended. All right, we're almost done here, but we now have to look at the logic that we needed to create in our code in order to have the desired effect. Our setup is the same as it was before, because the only thing we really need to do in our setup is to start the serial monitor, because we'd like to be able to see the text information coming in at the same time as we're listening to the audio coming out of our buzzer. So that's no different. Loop, however, is going to be a little more complicated than before. So let's have a look at what's going on in loop and try to sort of scope it out. The first thing we do is we introduce a new integer variable called tone frequency. It starts off as 0 because when there's no buttons being pushed, we don't want any sound to be coming out. But we'll change the value of tone frequency to a different value depending upon what button is pushed. Next, we have something that'll look familiar to us. We use the Getkey function on MyAwesomePad in order to return a result if a button is pressed. So if a button is not pressed, the result of Getkey is just a 0 or false, and so nothing will happen when we say if result. On the other hand, if a button is pushed, result will be the corresponding button, it will be the corresponding key character corresponding to that row and column which was pushed. That's familiar to us, but we're now going to do a little bit more with it than just print the number out on the serial monitor than what we did in our last session. So the next little piece of code here involves something that you may have seen before, or perhaps not, and it is two nested loops, a for loop inside of another for loop. Let's look at this a little bit carefully and see what's going on. On the outside here, I have a for loop that basically allows the variable j to go from 0 to 3. Since rows is 4, and this stops when j is equal to 4, it will go 0, 1, 2, 3. Inside that loop, which goes from here to here, we have a second loop, and this lets the variable I also go from 0 to 3. That is, I equals 0 to less than columns. So you can see that by having these two loops, one inside the other, I'm going to interrogate every possible combination of I and j, from I and j both equal to 0 up to I and j both equal to 3. And in that process, I'll have examined all possible combinations of row and column that might have been pressed. One of those is going to be the one that actually was pressed. So what we do inside these two nested loops is we put an if test. The if test says, well, result was not 0. What was it? If result is equal to buttons of j and I being the value that we're looping over right now, then that's a hit. That's the one that got pressed. And so if that's the case, make a note of it. Write down or take I and j, that particular value of I and j, and see which tone that corresponds to. And put that into tone frequency, the variable that we defined as 0 up here. And so what will happen is we'll loop through all the possibilities. If it happens to be that we pressed the first button, 0, 0, then we'll get a hit on the very first try. But if we pushed a button somewhere in the middle, we'll have to loop for a while until we get result equals buttons and then set the appropriate frequency. So in any case, after looping through this a maximum of 16 times, we'll get a result and we'll drop out at the end of both of these loops. The only thing that's left to do now is to use that information for our output. The first part of this will be familiar to you because we're just going to take the results of this search and we're going to send it out to the serial port. So here you can see we use the serial.print command to simply print out key results. So that'll tell us which key was pushed. And then we'll put out frequency and tone frequency. So we'll see the numerical value of the frequency that was selected by that key. So far, though, we're not hearing anything. And so the final part of the code here is to actually now activate the buzzer. And this will be using the new function, new to us, tone. Tone takes as its arguments the line from the hero, in this case that's buzzer, or 10. Tone frequency, so this is how rapidly to turn the square wave on and off as we are sending it to our passive buzzer. And then finally 500 milliseconds, which means leave the sound on for 500 milliseconds and then stop. So this will give us a half-second long buzz or beep at the frequency selected by the button that we press. We throw in here a delay of half a second and then a command no tone, which basically turns the buzzer off. You may be thinking that's a little redundant because the buzzer already turned itself off after half a second, and that's really sort of true, but it might be a good habit to get into using the no tone function here because, for example, if we had more than one buzzer and we wanted to command those with different pins on the hero, you can't command another buzzer on another pin to make a sound until you turn off the sound on the buzzer that you were just using. So while it seems a little redundant, it's not a bad idea to throw the no tone in there to turn things off. Now you'll notice that what happens is at this point we reach the end of loop, or actually we reach the end of result, but then dropping out of that we reach the end of loop and the whole process just repeats over and over again. If no button is pushed the next time through, nothing will happen. If a button is pushed, then we'll get the results of which button was pushed and the corresponding sound in our serial monitor and in our audio output. So with that little summary of the code that we have here, we should be able to go ahead and try this out and see if it works. Let's first of all compile the code and make sure there aren't any syntax errors in it. So let's verify it. And it looks like we did okay this time. We didn't forget any semicolons or any unmatched brackets. So that looks good. So let's go ahead then and upload the code. We shouldn't expect anything to happen until we press a button, because if no buttons are pressed, then the keypad commands will return a 0 and nothing will happen. Okay, uploading should be finishing here shortly. Okay, it's done uploading. We have no sound and no output yet from the serial monitor. So let's go ahead and let's try and press a button. Let's say I'll press button number 5. And we got key 5, frequency 311 Hertz. Very good. Let's try the next one over, button number 6. Okay, that worked correctly and the tone sounds a little bit higher. Let's do the next one over from 6, which would be B. Okay, So this seems to be working pretty well. The lowest frequency should be key number 1 in the upper left-hand corner. And you can see that's a low one. A little bit higher frequency, 93, and so on. I can go down to the lower rows and see what some of those high frequencies sound like. The star key, corresponding to frequency 523 hertz, or rather 1397. Let's see if we get that on the screen there. Here's the next one over, the 0, corresponding to 2637. And we can go up to the very highest, 3729. All right, so we have apparently succeeded in being able to generate frequencies using our hero and using the passive buzzer. So with that, we've reached another milestone and are ready to continue working on some of the tasks that we have to activate and secure our rescue shuttle. So for now, remember, build everything and invent safe.